when you apply force is majorly that when you apply force, something will start moving, for example. You can now also talk about the direction. Principle of moments. So when the total clockwise moment is equal to the total anti-clockwise moment, just to give you an idea, like I have this pen, very important, just as I was saying, till the center of gravity is such that hello students, welcome in today's class. In today's class, we are going to talk about turning effects of forces. You do understand that we are following a sequence where we are discussing the various effects of forces, and this video is again a part of that sequence. So what are we learning today? Turning effects of forces, one more effect of force. So put down the heading turning effects of forces and then we will start. Okay, so the first thing that comes to your mind when you apply force is majorly that when you apply force, something will start moving, for example. You might have a table in front of you. When you apply a force on that table will start moving, right? But can you also expect something not to move but rotate? So take for example this pen. This is in my hand and what I do is I apply a force. You won't say that the pen is moving. It's not moving, it is still in my hand. But what is it doing? It is rotating. It is turning. That is what we are going to learn today. Turning effect of force or the rotating effect of force. It's not moving. If I apply a force like this, this is moving. But if I apply a force like this, then this is called the turning effect of force. But for that you always would want to talk about some point is fixed about which the body is rotating. So this is about which the body is rotating, the pivot or the hinge about which this pen is rotating. Okay, so one by one, don't worry, we are going to start talking about these things. So first thing that I wish to talk about is a force acting on an object can cause the object to turn. So that's the topic of the day. To produce a turning effect, the force must be applied at a distance from the pivot. So by taking this as an example, I think you should be able to understand this, that if you apply a force on the pivot itself, where the thing is fixed, the object is fixed, can you expect it to rotate? No. You can only expect it to rotate when you apply the force slightly away from the pivot, right? That's the basics of it. You can take an example for this, like door. So what you do is you pull the door handle, then the door rotates about the hinge that you have at the other end. Can you expect to rotate this door by applying a force at the hinge itself or the pivot itself? Answer is going to be no. Okay, so that is very important. The force must be at a distance from the pivot. Next, moment of a force is defined as the product of the force. So now I will talk about the technical definition. See, understand. Let's say this was the pen, okay, and we were applying a force here. And this is the point about which this pen was rotating. And therefore, this is the distance or the perpendicular distance at which this force is applied. So this moment of force, which is basically the turning effect of force, should be proportional to the force in the first place. More force you will apply means more turning effect. So if I apply a greater force, would I not expect a greater turning effect? Of course, yes. Then this moment of force is also proportional to the distance. Now think about it. Here we have the pivot or the hinge. If I apply the force very close, it does not rotate that much. But if I apply the force at the end, then it's easily rotating. It's creating more turning effect. That is why the door handle here is far away from the hinge. The door handle, if it is at far off distance, you get more turning effect. So that's what I have written here. Moment of a force is defined as the product of force and the perpendicular distance. So this is force times perpendicular distance, and that is why the unit should be Newton into meter or Newton meter. Some people also call it torque. So just for the sake of knowing it, moment of force is also referred as torque. So you might have heard of this particular term in context of cars, etc. So torque is basically the rotating effect that is generated by the engine or stuff like that. So torque is also something that you can alternatively use for this, but we will go with the terminology of moment of force. Okay. So you now understand what are we learning today? The rotating effect of force. So that's one new thing that we are going to learn today. Okay, I will wait, you copy down the important information, then we move forward. Alright, so now moment of force, force times perpendicular distance. You can now also talk about the direction. So if this pen was here and I applied a force like upwards, then it's rotating like this. What do you call this? Anti-clockwise. Okay, so if the clock turns like this, then it's anti-clockwise. Okay, while if you apply the force like this, then it is like clockwise. So keep that in mind. There are two ways of specifying the direction of turning effect. One is clockwise, the other is anti-clockwise. Okay, so since it is possessing a direction, direction becomes important. It is a vector quantity. Okay, its direction can be clockwise or anti-clockwise. Rest I have explained to you. That's what I have written, the two sense of moment that you can have. You can copy this down or just write it very briefly, that there are two possible directions, clockwise and anti-clockwise. Okay, next let's do a numerical. The minimum moment to open a door is 25 Newton meter. Okay, the door must be opened with a force of 60 Newton at the handle. Calculate the minimum distance. Okay, so as you know, moment is equals to force times distance. Okay, perpendicular distance. So we are applying, let's say, the force here, and the perpendicular distance is d. So they are now telling us that you need a moment of 60 Nm Newton meter to rotate this, and sorry, not 60 but 25. You need a moment of 25 Newton meter, and the force that you can apply is 60 Newton. So they are asking us the distance. So now they are asking us the distance. So this distance is going to be 25 over 60. That's going to be 5 over 12 meters. So let's quickly do this calculation. 5 divided by 12 is going to be 0.42 if I round it off to two significant digits. Okay, or you can call it as 42 centimeter also. So easy, simple question. You just have to use the formula. Moment of force is force times perpendicular distance. But it's not only about the formula. Are you able to correlate with this is very important. That you apply more force, it's more turning effect. If you apply it at a greater distance, then also it is a greater turning effect. Okay, copy this down, then we move forward. Okay, next, principle of moments. So when the total clockwise moment is equal to the total anti-clockwise moment, there is no resultant turning effect. So it's just like when you say net force is 0, that doesn't mean that forces are not acting. It might be balancing. Same is here, that if we say something has no moment acting on it, then that might mean that two moments are cancelling out each other. For example, the steering wheel, let's say it is hinged here. Okay, when will it rotate? How does a steering wheel rotate? Let's say you want to turn left, so you will apply a force here like this and force here like this. So what is happening? Both the forces, this is also rotating it anti-clockwise and this is also rotating it anti-clockwise. So the anti-clockwise torques are adding up. Okay, on the contrary, let's say if I make it like this, so this force wants to rotate it clockwise and this force wants to rotate it anti-clockwise. So if the clockwise and anti-clockwise torque balance off each other, like they are equal and obviously they are opposite, then we call it as the principle of moments, and that is when we say that it is not going to rotate. Okay, keep that in mind. So if we say that anything is in equilibrium, so it should always mean that it is not moving and it is also not rotating. So for example, a fan is rotating, so you can't call it an equilibrium. Maybe a chair in front of you can be equilibrium because it is not moving also, it is not rotating also. So the condition for anything to be in equilibrium is that there is no resultant force and there is no resultant moment. Force should also balance and moment should also balance. So is the moment balancing here? Yes. Is the force balancing here? Yes. But where is the third force? The third force is maybe the force applied by the hinge, that the steering wheel is hinged at the center. So that will balance off these two forces. So the net force also becomes 0 and the net moment also becomes 0, because whatever moment this will produce clockwise is balanced by whatever moment this one is going to produce anti-clockwise. What about this one? This will not produce any moment. Why? Because it is passing through the pivot only. So this will not produce any moment whatsoever. Okay, easy. Write down what is the principle of moments, then we move forward. Alright, next. So let's do a question very quickly. A man holds a stiff fishing rod with two hands. A 20 Newton fish hangs at one end. So 20 Newton fish, that means it's the weight, it's already the force. Figure shows the positions of the man's hand and the fish on the rod, with the right hand as the pivot and the left hand applying a force. Okay, alright, so this is one hand and this is the other. So like he's holding it like this. Okay, the rod is held horizontal, stationary, okay, and very light. So there is no weight of the rod such that the effect of its weight is negligible. Calculate the force F. Okay, so about the pivot, let's say about the pivot, let's call this as the pivot. Let's equate the clockwise and the anti-clockwise moment. Okay, clockwise moment is equals to anti-clockwise moment. Alright, let's do it very quickly. Clockwise moment is equals to anti-clockwise moment. So what is the clockwise moment about the pivot? So this thing is going to rotate this clockwise. That's going to be 20 times 1.2. Can you understand why 1.2? Because from the pivot this distance is going to be 0.3 plus 0.9 should be equal to the anti-clockwise moment. So that's like F times 0.3. Okay, so the value of F is going to be 80 Newton. This will cancel out 4 times the value of F. So what is his hand applying here? A force of 80 Newton to balance this fish off and keep the fishing rod horizontal. Copy this down, we move forward. Very easy, no big deal. Force times perpendicular distance is all we need to understand, and second judgment that we have to make is either it's clockwise or anti-clockwise. Alright, let's take another one. Okay, the person on the left in the figure has a weight of 400 Newton, okay, and is at a distance of 2 meter to the left of the pivot. 2 meter to the left of the pivot. The person on the right has a weight of 700 Newton. So this is what I'm showing, the force, and this distance is what they want us to find out. How far should the right person be so that the seesaw is in balanced state? So again, who's applying anti-clockwise and clockwise moment? This person is applying clockwise moment, this person is applying anti-clockwise moment. So let's balance it off. Anti-clockwise moment is equals to clockwise moment. Very quickly, anti-clockwise moment is going to be 400 times 2, and that is equals to 700 times d. Okay, so this value is going to be 800 divided by 700. So this value of d, if we round it off to, let's say, 3 significant digits, then it's going to be 1.14 meter. That's the answer of the problem. One more thing I wish to answer here. What is the force applied by the pivot, okay, at the fulcrum? So this point is called the fulcrum. Okay, what force is applied by this pivot? Okay, the contact force here. So what would you write? F is equals to upward equals to downward. Here we are writing clockwise equals to anti-clockwise. Now we are going to write upward equals to downward. So F is equals to 400 plus 700. So that's going to be 1100 Newton is what this pivot is going to apply. Copy this down, take a screenshot, we move forward. Alright. Next, a uniform meter rule is balanced at its midpoint. Okay, so this is a meter rule, 100 centimeter. Calculate the distance d1. Okay, so this is balanced. We have to calculate the distance d1. Okay, so this distance d1 is obviously 30 centimeter. Why? Because the first weight is at 20 centimeter mark and the pivot is at 50 centimeter mark. Okay, calculate the moment of 10 Newton weight. So we can do this part. So d1 is 30 centimeter. Let's calculate the moment of this 10 Newton. So the moment is going to be 10 times 20 centimeter. Sorry, this distance is 30 centimeter from the pivot. This distance is 30 centimeter. So let's keep it as 0.3 meter. So this makes it 3 Newton meter. The ruler is in equilibrium. Then find the position R. So this is in equilibrium, again using clockwise moment is equals to anti-clockwise moment, and since we have already calculated the anti-clockwise moment, that is how much? That is 3 Newton meter. So just equate this to 8 times the distance d2. Okay, so this value of d2 turns out to be 3 by 8. Okay, 3 by 8. So that's 0.375 meter, which can also be written as 37.5 centimeter. But remember, this distance is 37.5 centimeter from 50. So this is 50 mark. This is again 37.5 more. So the position of this should be referred as 87.5. This should be referred as 87.5 just for the position. They're not asking us the distance, they're asking us the position. So be very careful what they are asking. Okay, copy this down, we move forward then. Alright, figure shows the forces on a pole AB lying horizontally on the ground. Calculate the minimum vertical force. So now they are asking us the force. In the previous one they were asking us the distance. Okay, so this has to be lifted like this. You have a rod, you are lifting it. So that means you are rotating it about this point. Okay, so this is going to be lifted. Who's stopping it from being lifted? Of course, its own weight. So just to lift it up, we will write moment that is anti-clockwise is equals to the clockwise moment. So this weight is trying to keep it on the ground, and now you are lifting it off the ground. So can you imagine, about A you are lifting it, and that is what they are asking. Okay, to lift the pole about A. Okay, so what are we going to write? So we will write anti-clockwise moment is going to be F times 10 and the clockwise moment is going to be 800 times 4. Okay, so this F is going to be 80 times 4, that is 320 Newton. So what force do you need to apply here? 320 Newton, and it is less. It is less. That is how we can sometimes minimize our effort. Okay, we can minimize. So if for example we have to lift a heavy object, understand this, if we have to lift a heavy object, then what can be done? So that heavy object can be pushed, put here, we can put it over here, that can be called as load that we have to lift, and we can apply a force here. So if this is a longer arm, then in smaller force we will be able to lift the load. Okay, in smaller force we will be able to lift the load. Let's keep it this way. Okay, so by applying a small force we will be able to lift this load. How? If we keep this distance large. So if we apply the force at a larger distance from the fulcrum, then by using that small force we should be able to lift heavy objects. So these were the techniques that were used long time back. Now we have hydraulics and stuff like that, but earlier we used to make effort like these and minimize our the requirement of force. Okay, copy this down, then we move forward. Alright, next one is center of gravity. So I won't be talking much about it, just to give you an idea. Like I have this pen, you know, its weight is acting somewhere, and if I somehow figure that out and I am able to balance this on my finger, then that is the center of gravity. Okay, if I am able to do it like here, right here. Okay, so what is center of gravity? It is the point through which the weight of the object acts. Okay, when the object is balanced, so of course when you are balancing it here, then the entire weight is passing through the fulcrum, so there is no rotating effect. Imagine if I try to balance it here, what's going to happen? If I try to balance it here, the weight is going to, you know, rotate it or topple it or whatever you may call it. Okay, so that's center of gravity, the effective point where the weight of any object is acting. Okay, next, for regular shaped objects, of course, these are the geometric centers. So this is not regular, so it's like tapering, it's narrow here, it's blunt here, so it's not uniform. If it is uniform like this meter scale, then you can obviously say that the weight is going to act right at the center. But if it is not balanced, then it can be slightly away from the geometric center. But if you have regular shaped objects with symmetric configuration, then the center of gravity is always at the geometric center. For example, these shapes, a rectangle, a cube, a triangle, you can expect the center of gravity right at their geometrical center. Next, very important, just as I was saying, till the center of gravity is such that the weight is passing through the base, the object will be able to sustain itself. What do I mean by that? Take for example these two configurations of a cone. So when the cone is positioned like this and when the cone is positioned like this, what do you reckon, where the cone can be stable? Of course, you know, right here, this configuration is not stable, because even if you topple it slightly, its weight, like even if you like turn it slightly, its weight is going to topple it. But if you talk about the other configuration, let's say you try to have it like this format, then what is going to happen? The weight is going to be here and it will in a way, you know, balance it off again, push it down on the ground again, and the weight is still passing through the base. Okay, this is what I have written. An object will not topple if the weight of the object passes within its base. So it will again come back, it will again become stable. But if you know, keep bending it, keep bending it, keep bending it, and you know, it bend it so much like this that the weight goes out of the, let's say weight goes out of the base, then it is definitely going to topple. Just for your information, just for your information. So for example, this configuration of this slab is not stable. You twist, you tilt it slightly and the weight is out of the base. Base is here, weight is here, it's definitely going to topple. But now here, you know, this configuration is very stable. Even if you topple it a little bit like this, still the weight is going to be within the base. So just keep it in mind that center of gravity is very crucial, because that's going to decide how, you know, stable any object is, and there are lesser chances of toppling. So that is, you know, something that even designers of different buildings or let's say vehicles like cars, aeroplanes, all these things are to be kept in mind where center of gravity is acting. These things become very important. Later on we will talk about these things in detail, and if you will opt for physics in your further classes, you will understand this in very much detail. But right now I don't want to confuse you much here. Just keep two things in mind. Center of gravity is the effective point where the weight acts, and it has to be within the base if the object is not to topple. Otherwise, if it goes out of the base, then it is definitely toppling. Okay, all right, still write this one line, then we move forward. Okay, so I have taken one last example here, and then I will almost be finishing off with the entire unit of forces, and then start with the previous year questions. So last question for this particular class. A student wants to measure the weight of a uniform meter rule. She hangs a weight of 2.5 Newton as we can see. Then she adjusts the position of the ruler on a pivot until it balances perfectly as shown. Okay. So obviously the weight is acting at 50 centimeter mark. This is where the center of gravity is, what we have learned. Okay. So what is the weight of the ruler? Okay. So clockwise torque is equals to anti-clockwise torque. This distance is 10 centimeter, of course, 70, 80. While this distance is going to be 20 centimeter. So can you understand that if you want to balance off this somewhere else than its center of gravity, like what is being done here, then you will need to balance it by applying some another force somewhere else. That is what they are doing. They are balancing the meter rule not at its center of gravity. If this meter rule has to be balanced only by itself, then you obviously put the pivot right at 50. But here we have shifted it to 70, so you need to apply another force to balance it off. So very quickly, 2.5 times 10 is equals to W times 20. So the value of W turns out to be 25 over 20. So that's like 5 by 4. That's like 1.25 Newton. And you can also answer again, what is the force applied by the pivot at the fulcrum? So you would say F is equals to W plus 2.5. Upward equals to downward. What is the downward force? W is 1.25 plus 2.5. So that is going to be 3.75 Newton. That's the answer. If someone would ask, okay, that what is the force applied. But I hope you've understood what center of gravity is. Even in numerical problems, they might give you that, imagine the center of gravity is this particular point. So you have to show the weight of that object, the downward pull of gravity at that particular point. Keep that in mind. Okay. So that's all. That's all about this whole unit that we have discussed about forces, springs, okay, turning effect of forces, all these things that I have talked about. Okay, F is equals to ma. That was my effort. I hope you were able to learn and understand things. And now we will be coming up with the previous year questions. It's going to be very exciting. And that is where you actually learn things, when you apply them in the questions. So the application part is the real way of learning things. So I've given you a basic thing, like given you the fundamentals of everything. Now we will be using those fundamentals to do the previous year questions. I am very excited about it. I'll be, I would talk about all the various core, extended, different sequences, but all that is going to happen in the next video. That's all for this one. Happy learning. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.